Okay guys, this is take 2 of Volumes by Slicing Part 1 because I noticed 2 errors that I made. And if you already watched that video, you may have noticed them too. So that's what happens when I do like 20 videos an hour. I'm sorry about it. So I didn't want there to be any discrepancy, and I'm not that good at editing, so here we go. If you didn't watch the first one already, well, good for you. You don't have to listen to it a second time around. All right, so we're going to talk about volumes by slicing, or as it's also known, volumes of known cross sections. And your keywords here are when you see base of a solid. All right, that's when you know you have to use volumes by slicing. All right, and the steps I'm going to go over again. Number 1, you want to make a sketch of the scenario. Let me make this bigger. You want to make a sketch of the scenario. The second thing is AP is going to give you the cross-sectional slice. All right, what you're interested in is the area of the cross-sectional, the face of the cross-sectional slice. So, you know, if AP tells you, you know, the base of a solid is in the plane, its cross-sections perpendicular to whatever axis is a square, then you know that the area formula geometrically for a square is side squared. All right, so, you know, if it's a circle, it'd be pi r squared and so forth. All right, you're going to determine your limits of integration. Sometimes they're given, sometimes you have to figure them out. The most difficult part usually is the width, or you can call it length. You can call it whatever you want. Generally, we call it width, and I'll talk about that in a second. And then the easy part, so this is easy, this is easy, this is probably going to be the most difficult part. The formula for the volume by slicing on the x-axis anyway, or perpendicular to the x-axis, is the integral from a to b of the area in terms of x dx. And in the last video, I had said that you guys are only going to slice perpendicular to the x-axis, and that was my IB brain talking, because in IB they don't do slices perpendicular to the y-axis, but in AP they did. But remember, I didn't teach to AP, I taught to IB, and they still all passed with flying colors. So anyway, it's not something that I necessarily teach because it wasn't on the IB exam. Okay, so you will be doing both axes, but I'm going to stick to, for today, the volume between a curve and the x-axis, and then the volume between two curves where we're cutting perpendicular to the x-axis. All right, so we've got our formula, and the other thing is I want you to write this down in your notebook. This is the area of an equilateral triangle. It's the square root of 3 divided by 4 times the side squared. AP likes to use this, and they don't give you the formula for that, and you're not going to have time to look it up or whatnot. So just write it down somewhere, put it on the cover of your notebook or something so you have it in case you need it. That's all I'm going to say about that. All right, so what I did was I found this little GeoGebra program because it gives a really nice depiction of what the slices look like. Now look, I understand that sometimes you kind of trying to visualize what the solid looks like. That doesn't matter. Don't worry about what it looks like at all. What's important is what is the cross-sectional slice. So here we have two functions in the plane, all right? And how you would see it, like on an AP exam, is like this. And in fact, you wouldn't see that. You would see it shaded in, okay? So on your AP exam, you'd see a picture that maybe looks like something like this, all right? So it's just going to look flat, topological view. But in reality, you know, if this thing is, if the cross-sectional slices, if we slice perpendicular, so let me remove these for a second. Stop spinning. If we remove these, go back here, these squares here, and the idea is that, you know, here's the x-axis, right? And let me just put 1 bar in there and change this to 1. So I'm going to put it here. This means I'm slicing perpendicular to the x-axis, all right? if I slice this thing perpendicular to the x-axis, there we go, and the cross-sectional slices are squares, then what I know is that the area of the face is side squared, right? Because the square, that's the formula. So the more of these, so I'm going to go all the way out to the tip here. I just want you to see that the square starts out really, really tiny, right? And it gets bigger as we get to the middle, and then it gets really, really tiny again. And you know, if I do a few slices, I'm going to get a pretty good approximation, or maybe a terrible approximation. But the more slices I make, the better I can approximate the volume. So to find the volume by slicing, we integrate the area function. And I'm not talking about the area of the base, I'm talking the area of the cross-sectional face, right? Because if you think about it, if I know this area and I know all those areas, and I add them all up, I'm going to get the volume. Because there's so many slices here, they're so thin that it's almost as if the width doesn't exist, okay? All right, if I change this to equilateral triangles, well, there's a couple in there. Again, the slices are perpendicular to the x-axis, and the length or the width, so we call the width the distance between either the curve and the x-axis, or in this case here we've got area between two curves, so the width would be top curve minus bottom curve. That would equal the width, or sorry, the length of this triangle side. Okay, and again, the more we have, the better our approximation. Maybe our cross-sectional slices are semicircles, right? And so, boom, there's our solid. Okay, so again, it doesn't matter what the solid looks like. What matters is that you know the cross-sectional slice, and AP is going to give that to you, and that you know the area, the basic geometric formula for the area of the face of a cross-sectional slice. Okay, so let's do the mathematician's paperweight problem, and I've got the Finney book here, and it's a cute little problem. I couldn't find it online. I actually looked. Here it is. So I don't know. I figured it'd be posted somewhere on Google, but it's not. And I'm not going to put the book under because I have a very slim desk. It's very minimal, so I don't have a lot of room to move, you know, back and forth this way. So anyway, to avoid my aggravation, I'm just going to read some things. What we have is a mathematician has a paperweight made so that its base is the shape of the region between the x-axis and one arch of the curve y equals 2 sine of x. Okay, so what I have is a function 2 sine of x, and the other thing that I have is a picture, okay, in the plane, and it goes from 0 to pi. So what I know is that my limits of integration are from 0 to pi, and the area of this region is between this curve 2 sine of x and the x-axis. So right now I don't have an issue where I've got, you know, a region between two curves. That's even better, okay? And what they're telling us here in the book is that cross sections perpendicular to the x-axis is a semicircle. Okay, the area of a circle is pi r squared. So that means the area of a semicircle is pi r squared divided by 2, right? Let me make this bigger. That way I can see if I'm going off the page. Okay, so I have my basic geometric formula, I have my function, and I have my limits of integration. The problem here is that this is not in terms of x, this is in terms of r. Now, if I'm slicing perpendicular, you know I can't draw. This line is perpendicular. This is the diameter of my semicircle, right? And the diameter, or this length or width, if you will, so remember the semicircle is going to come out of the page, right? This length here, or diameter, is just the function itself. So when you have a curve and the x-axis only, the distance between the curve and the x-axis is the function itself. So the diameter of this semicircle is 2 sine of x. But we need a radius, right? I need to get rid of this r, and I need to change it in terms of x because I need a of x. Well, we know that the radius is the diameter cut in half, right? So my radius is the sine of x. So what I'm going to do is I'm going to take this formula and I'm going to rewrite it as a of x. Very important that you write down a of x is equal to pi times sine x squared over 2. And if you want, you can pull the constant multiple out and write it like this. Okay? Well, guess what? I have an a of x, I have my limits, I can integrate. I say the volume is equal to the integral from 0 to pi of sine squared x dx. Now look, I'm going to pull the pi over 2 out here because it's a constant multiple. And I'm not going to rack my brain trying to use u substitution or anything like that, because you're allowed to use your calculator and your notes for the entire test. Rather than that, I'm going to graph this thing and I'm going to let my calculator do the work. And to do that, here we go. Let me just move that over. To do that, I'm going to do pi divided by 2. I'm going to put a parenthesis. I'm going to put the sine of x. And I'm going to square that quantity and hit the graph key. And when I do, from negative to positive infinity, we see this little wiggle worm. All right. And if you want, you can zoom in on it or whatever. There's no need to. All you need is an answer, right? And since they know you're using your calculator for the whole task, then use your calculator. You're going to use second calc 7 from 0 enter to pi enter. And when you do that, you're going to see that region shaded in, and you're going to get a volume of 2.467 cubic units. Now again, as I said in the last video, this was actually they gave us units in inches, okay? So following with the example, if AP does not give you units, you don't have to include units. Oops. But if they give you units, then you need to include them. Since this is volume, it would be cubic inches. So the volume is approximately equal to 2.467 cubic inches, remembering that you have to round to 3 places past the decimal with AP. Okay, so then what I said in the last video is, well, how about we have the same function, but now instead of having semicircles as our cross sections, our cross-sectional slices are squares, right? So what if my cross-sectional slice is a square? Well, I have a new formula, right? So I still have the function, I still have the same interval, but my area formula is side squared, and the length of the side of the square is just the function itself. So a side is 2 sine of x. So now rewriting this in terms of x, a of x is equal to side squared, right? And, you know, you could write this as 2 sine square x if you want to, because you're not going to do anything special with it because your calculator is going to do all the work. So we would say that the volume is equal to the integral from 0 to pi. I can pull the 2 out front and do sine squared of x dx. What I did before on this is I pulled a pi out here. There's no pi in the area of a square. So anyway, again, I'm going to do 2 times the sine of x squared. So in my calculator, I'm going to hit the graph key. I'm going to wait a minute. And I'm going to do second calc 7 from 0 enter to pi enter. It's going to shade in the region, and hey, look at that, the volume is pi. It's 3.142, so I'd say the volume is approximately 3.142 cubic inches. Make sense? If that were, say, an equilateral triangle. Well, if this is an equilateral triangle, oh, this is terrible. I know it's terrible. Well, you can't see it, so that's probably even better, but I went off the curve. But if I cut perpendicular and I'm getting equilateral triangles as my cross-sectional surface, then this width here is the length of the side of the triangle. Well, the formula for the equilateral triangle is, so my formula is root 3 over 4 side squared. The side of this thing is 2 sine x, so my area would be root 3 over 4 of 2 sine x quantity squared. That would be my a of x. Again, if my limits of integration were the same, I would say the volume is equal to root 3 over 4, again pulling that constant multiple out. And you know, you could even square this, right, and write this as 4 sine squared and pull the 4 out too. Actually, I'll do that. So that's not volume yet, and so those 4's would cancel, right? So volume would be equal to root 3 times the integral from 0 to pi of sine squared of x dx. Okay, and then I could get an approximation for the volume. All right, let's do area between two curves. So earlier, let me see here. Here. So let's see. AP, FRQ, volumes by slicing. And I don't know. Let's just choose this one. So I think we did this problem in class. This is quintessential, and I'm just going to blow this up. Well, right away, what I want you to notice about this is, you know, we're not finding the area, okay? We're not going to worry about spinning it right now or anything. Part C, the region is the base of a solid. That's my red flag that I need to deal with volumes by slicing. And not only that, it tells me that the cross-section perpendicular to the x-axis is a square. So what I know is if I cut this thing perpendicular to the x-axis, I'm going to have squares, right? So my area is side squared. Now my functions are pretty rough. They're sine pi x and x cubed minus 4x. So this is definitely a calculator problem, all right? And my limits of integration, it's always the domain. It's going from 0 to 2. So here's my interval. I have my limits. The only thing I have to do is write my area function. So, and again, it's really important that you write a of x. Do not just write area for the greater. Write a of x in your work. That's going to equal to, well, now look, this is a little bit different, right? Because this isn't between a curve and the x-axis. This is a width here between two curves. It's no big deal. It's top curve minus bottom curve. So what you're going to have is, this is going to be the sine function. You can clearly see this one's the sine, but you could graph it if you wanted to see. And then this one here, of course, is going to be the cubic function. So the top curve is the sine of x, pi x, minus the bottom curve. And what you need to be really careful of is, please don't distribute the sine. Just leave it alone, okay? If you have this as your integrand, you're golden, provided that your limits and everything are correct and that you don't forget your dx. So if I want to find the volume of this thing or approximate it, I'm going to say volume is equal to, and I forgot to square it. Shoot. Sorry. See, I get carried away and I get anxious to get this video over with because it's been, I gotta learn how to edit. I've never edited a video, I don't think ever. So I'm not used to this, but sorry. This is the length of the side, right? So side squared would be that. So volume will be the integral from 0 to 2 of this nightmare. And again, don't expand it out, just leave it alone. And why? Because your calculator is going to do that for you. Throw that thing into your calculator. Now this is another battle, putting it into your calculator correctly. All right, so let me just do this one. so that way you can see. All right, I have an outermost parenthesis. So again, I'm going to put this thing in exactly how I see it here in my calculator. So it's not that hard to do if you just write it out correctly, then you won't have a problem. So it's the sine of pi x, close that parenthesis, minus parenthesis x cubed minus 4x, close the parenthesis, close the outer parenthesis, and then square it, right? And hit the graph key. And when you do that, ooh, craziness function. Now you're at the point where you can integrate. So you can use your second calc 7 from 0 to 2. And it will shade that region in, and you get 9.978 as your volume. All right, and this doesn't have a scoring with it. Oh, yes, it does. Here it is. And look at that. Here's the scoring rubric. You're getting a point for the correct integrand. You noticed it's not all expanded out. We don't do that in higher math. We have the correct limits. We have our dx. And we have the correct answer because our calculator did the work for us. Pretty neato, right? Okay, so whether it's between two curves, which again, you know, if you're finding the side of a square or whatnot, if it's top curve minus bottom curve, or if it's just between the one function and the x-axis, which the length of that so the length of that cut, I guess, or cross section would be just, you know, the function itself. These are pretty simple to do, especially when you're cutting perpendicular to the x-axis. See if there's another one. Oh, look at this. This is student work. So I don't know if they've given this kid a 1, 2, 3, 4, 5, but in this problem here for C, they might have docked the kid a point because you're supposed to round to 3 places, so they probably would have docked the kid. I'd have to look at the commentary on it. It's fun to read them. And the commentary, oh, hey, look, here's the commentary. So let's see if they docked him. No points in part C. In part C, student integrates a difference of squares rather than the square of the difference. The integrand point was not earned, and the student was not eligible for the answer point. Why? Because the student didn't round. So, actually, this is good that I brought this up. So, this is what comes out in your calculator, maybe more. Remember, they're not going to give you the point. They have no problems with holding points at all in AP. So you're going to want to make sure you round properly. So to 3 places past the decimal or to the 4th place. So you could put 9.9783 and you would be fine. If you round improperly or you jot down the whole number, you're going to have a problem. Okay, you're going to lose points. Anyway, pretty cool. So you can find these all over the net. If you look at what I Googled to get this, you know, I just Googled APFRQ volumes by slicing and brought up, you know, a problem. I could click on any one of these probably. And look, student notes even. So keep that in mind that you can find some extra practice problems other than the ones I give you just by Googling it. Google's wonderful. All right. Now, is there anything else I need to cover in this? I remember in the last video I showed this. I did the mathematician's paperweight. Let's do just one more. I think I had done another AP problem, a different one that I pulled up somewhere. All right, so let's see if I can find one more. Okay. So these problems are long. I don't know. I won't bore you with any more details on this because there's a lot of volume. So if you've forgotten a lot between volumes of rotation, disc method, washer method, and slicing. You've got a lot to do already. So as I posted earlier, I don't want to overwhelm you with a bunch of stuff. I'm going to stop this video here. If you have any questions, please make sure you let me know, because if you don't ask me, then I don't know you have a problem. And because you're BC, I have a tendency to say, they get it, because, excuse me. Oh no, excuse me. I don't have COVID. But I have a tendency to sort of say, they're BC, so they get it. So if you don't tell me there's an issue, then I don't know. And I want to help you, and I want you to pass, but you guys are really quiet. So anyway, please ask me, send me a message through EDSB, and I'll be more than happy to help you. And please practice these, because your test is in technically like 9 more days or something. So we're getting down to the wire. All right, have a good night.